Here is problem 6 of the test. If you need time to look over the problem and get a handle of it, feel free to pause. It's also helpful to have a copy of this problem open on another tab. And if you need this problem, it can be found on the Art of Problem Solving wiki. A link should be in the description. So for this problem, we first want to ask, what is the problem about? Well, looking at it, we have a system of two equations in variables x and y. There are logarithms with varying bases. 225, 64 in the first equation, and x and y in the second. There are two solutions to the problem: x1, y1, and x2, y2. And our answer format should be in the form the logarithm base 30 of x1, y1, x2, y2. So that is what the problem is all about. Now, what is special about this problem? Firstly, because we are dealing with logarithms, we have to make sure that every single logarithm is well defined. That is, if the input is 0 or negative, then the logarithm is undefined, and therefore our solution is false. Next, we have to check this inverse property. And the fact that we have these inverse logarithms is special. In the first equation, we have the logarithm base 225 of x, while in the second equation, we have the logarithm base x of 225. They are special, not is special. My bad. Now, what relations are there? What can we deduce from these special properties of the problem? Because all logarithms need to be well defined, we can actually impose several restrictions. For example, because we have logarithm of x in the first equation, we have x is greater than 0. We also have y is greater than 0 by the same principle. And lastly, we have x1, y1, x2, y2 must be positive as well. Though that can be found out because it's a product of x and y, which are positive. In our inverse logarithms, there's actually a property of logarithms that is follows. Basically, if we have x and y, the logarithm base x of y is their reciprocal, or 1 over the logarithm base y of x. So this is a helpful relation because it helps us establish a relation between the two equations. And having said that, we can now simplify the question. Dealing with logarithms is a bit of a pain, and it might be easier to notice something if we simplify the problem by making a change in variables. So because we have the reciprocal property, we have the motivation to let the logarithm base 225 of x be a, and the logarithm base 64 of y be b. And substituting in, this gives us the two equations, a plus b equals 4, and 1 over a minus 1 over b is 1. Now this is a lot easier to see and to derive formulas out of than our original equation, which was based on logs. So now we proceed to solving the equation. Our first equation is pretty nice because, well, we have b equals 4 minus a. So we can substitute into the second equation. However, the second equation also gives us another restriction in that a and b both are non-zero. Because if either of a and b are 0, then 1 over a or 1 over b is undefined, and therefore a and b cannot be a solution. So that's something we have to keep in mind. Now substituting in, we have the second equation becomes 1 over a minus 1 over 4 minus a equals 1. Or 4 minus a over a times 4 minus a equals 1. And because a and b cannot be 0, or a and 4 minus a cannot be 0, then a times 4 minus a naturally cannot be 0 as well. So therefore we can multiply both sides by the denominator and obtain 4 minus 2a is equal to a times 4 minus a. Which, after rearranging, gives us a squared minus 6a plus 4 equals 0. And since this is a quadratic, we can just solve the equation. A is equal to 6 plus minus the square root of 6 squared minus 4 times 1 times 4 over 2 times 1, 2. And this gives us 20 in the square root, and this means it's 3 plus or minus square root of 5. This is perfect because we have two solutions of a, which correspond to our original problem, which wanted two solutions. Now, what did we want to find? We wanted to find the logarithm base 30 of x1, y1, x2, and y2. Now, let's try to find what these solutions are. If a is 3 plus or minus root 5, then b, being 4 minus a, is going to be 1 minus plus square root 5. The minus plus because it's negative a, not positive a. And before, because we had the logarithm base 225 of x being a, then we have that 225 to the power of a, which is essentially 15 squared to the power of a, 15 to the 2a, and we have the logarithm of base 64 of y is equal to b gives us 64 to the b, or 2 to the 6b. And notice we didn't substitute in a and b here. The reason is that because we have already solved for a and b, it makes no sense plugging them in here when instead we can try to look for cancellation and save some work in the progress. So rather, this is x equals 225 to the power of a and y equals 64 to the power of b. Okay, so now we have our solutions. We want to define logarithm base 30 of x1, y1, x2, y2. If we express our two different solutions as a1, a2, and b1, b2 for 3 plus root 5, 3 minus root 5, 1 minus root 5, and 1 plus root 5, we have that this is 15 to the 2a1 times 2 to the 6b1 times 15 to the 2a2 times 2 to the 6b2. And it's nice to see that we can use another exponent rule to simplify this a bit, make it easier on ourselves. So this is 15 to the power of 2a1 plus 2a2, and 2 to the 6b1 plus 6b2. Now what is a1 plus a2? a1 is and a2 are 3 plus or minus root 5. Doesn't really matter which order they are, but their sum will be 6 because the plus root 5 and the minus root 5 cancel out. Similarly, for b1 and b2, they are 1 minus root 5 and 1 plus root 5. So adding them together gives you 2 because the root 5s also cancel out. So because a1 plus a2 equals 6 and b1 plus b2 equals 2, we have that this is logarithm base 30 of 15 to the power of 2 times a1 plus a2, which is 12, times 2 to the power of 6 times 2, also 12. And we can just simplify this. So this is the logarithm base 30 of 30 to the 12. Or rather, just 12. And that will be our answer. 0, 1, 2.